game actually got to name them. Big Boutte is a Highling cleric that we found in the game. It's a good name. And, the fact that he has 69 hit points is a coincidence, but it's still a pretty funny coincidence. We've entered the code. Because of your superior intellect and diligence, you have saved Kron and all of its warrants. This ship, created by the ancients, is a grand experiment designed to populate this distant world. Prepare to beam down in Might and Magic 3. It's here, on the floor. I didn't see it. Thank you, my friends. You have banished chaos and rejected the false path of uncompromising order. Under the weight of the evidence and from the skilled pressure tactics of your lawyer, Lucas breaks down and admits to their crime. Congratulations, Ace. I think we're having a real moment here. I've changed my mind. I can't give her up. You can have your money back. How could I sell something so dear? Then again, a deal's a deal, right? Right? Catch you later. Good luck. Enjoy. I'm out of here. Let's pick up the bottle of grog here. Pick up the root beer. Use the root beer with the jug. Apparently root beer works very well. We get to see an instant replay. And a view from the blimp as well. I wonder what would happen if I tore the leg off this thing. Ark.
You have a resume. Madre de Dios, es el Puyo Diablo.
Man, I'm ready for you.
Yeah. Here it goes.
Enter visualization request.
Let's try it in the other order.
Subject code accepted. 645231 recognized. Beginning message.
Grand experiment of the ancients to use the technology of elemental manipulation to create a completely viable ecological and social microcosm. This microcosm was then to be transported to a distant biosphere, Terra, to supplant its indigenous ecosystem. The need was acknowledged for a central controlling unit capable of compensating for expected anomalies.
Well struck. That looks like a fatal blow.
Yeah, die.
My death will not save you from our wrath.
Are you going to plug me into Link, sir? I hope you know what you're doing.
I have no idea what we're doing. And
Something is happening, I think. Yes, I'm gaining control. I found my destiny, Mr. Foster.
goals in the middle. Perhaps you didn't even need to know that. The yellow crystal is over on the left side, and the blue one is on the right side. Switch to Annie, have her pull the lever to close the trapdoor, have her push the switch on this side, switch to Zack, have him push the switch on this side. On our way through this wall. Another mini boss. Good evening. Welcome in. See if we can't get the chat up and working. Of course, it's downloading an update. Makes sense. Yeah, welcome in, guys. What we're going to do tonight is probably mostly planning. Might do a little bit of coding though. Where we are right now is that I've made some leeway, and the more I learn, the less I know. But roughly, I've gotten the text to appear on screen using the bitmap font that we were working on last stream. The reason we didn't get anything working last stream and I couldn't figure out what we were doing wrong is that the file obviously wasn't a mono bitmap. It was basically an indexed image, and in that particular case, the bytes are stored as RGB and then an alpha channel as well. So what we were attempting to read like a 1-bit image was obviously not. That's why we mostly got gibberish out of it. So after I managed to fix that little problem, I was able to get the code that we wrote, the C program, working, and then I made quite a bit of changes to it as well. There were things that we needed to be done so we could push this reliably. And, the original plan was to put the font into the VTC memory so we could just copy it to the correct location, and that's a fine concept in theory. The practice of doing that, however, is a little bit different because of the way the VTC works. Is that roughly we just make a new page here, and maybe I can just show this to you. Let's see if we can't bring the chat up here. There's the chat. We resize that so it fits properly. Seems about right. Yeah, looks right. So if I make an honest attempt of switching to the OneNote cam, does that work in practice? Yes, actually, largely seems to work. Surprisingly. Why is it? Okay, fine. So where's the mouse? It's here. The way the VTC works is that, and the memory in general works is that it's linearly progressed. Does one line. And then it does another line. And then it does a third line. And so on. And for drawing characters, this is pretty abysmal. And the way the character is drawn at the moment is that I start at the first coordinate that we have to place the text. I have a little routine that calculates and where you should place the memory pointer in case you want to print the letter at, let's say that we want to print it at x equals 4 and y equals 5. And I have some code that I can move the memory pointer of the VTC to that particular location, which requires storing some information in the memory register on the VTC chip. And then the memory pointer jumps to that particular location. And then what we do right now is that we draw the A basically like this. First we draw this as a first line, then we draw the second line, and we draw the third line, and we draw the fourth line, and so on. And eventually the A gets filled. There's a total of 8 rows down, but only 1 across. So this is not optimal, obviously, and the way this has to be done to be able to copy it like we were originally planning to do is even dumber. So if we were to try to copy this, because you can only copy blocks of memory and they need to be sequential, and obviously all you could do would be to copy the top line, and that's fine if you just want to copy a top bit of the A, but that's not really what you want to do. So it would move the memory downwards if you tell it to do so, but I failed to see how we could optimize it in such a way that this would work, because realistically what we would have to do is where's the text again? If we were to write a word, for example, like Hyperborea, the only realistically optimized way of doing this would be to write the first line of all of these characters first, and then go back and copy the entire word, and at least a word at a time, probably a line at a time, So you would have to take the entire line that you've written to screen and write the first line of every character in the line first, and then use the copy utility to move around the source to point that to the font, and the destination point that to the memory. The problem with that particular scenario is that for every single line you have to move the pointer in memory towards the font, because obviously the location of every character is different. So that would require a lot of calculation just to be able to constantly move between the letters. So that's slow, and I'm pretty sure that it's actually slower than just writing each character individually line by line and then going to the next one and writing it line by line and so on. Because the code to do so isn't terribly complicated, but it's also just very slow, because realistically, when you have some computer bitmap architectures, they're optimized in a column sort of way. So you could do this by a column instead of having to do this line by line like we're doing it here. And welcome in, by the way, Racing the Beam and Texas Footballer. So the problem with this whole scenario is that the feature that we want is the copy feature, because that's pretty fast, whereas actually writing to the memory on the VTC is very slow. For text, copying isn't really that effective because you keep having to constantly change everything around. If you have a large block of an image, for example, and you can just point it to the image and it can move the pointer down as it copies, that's pretty quick. So if you need to fill something with a solid color, or if you need to have a white bitmap in memory that you just want to drag down line by line to the screen, that's pretty quick. The text, however, is not. And the original plan was to put the font into the VTC memory so we could use the copy feature to copy it around, but that's somewhat unrealistic, because I don't see the benefit of doing so. So in a way, I've freed up 500 something bytes of RAM from the VTC memory, because the font doesn't need to be there. If we need to write every character, it might as well be in the C128 memory. There's no particular reason for it to be in the VTC memory. We don't need to waste the memory there to be able to write it. And take a look at this code. Where's the... Here it is. Well, here it isn't. There it is. So what we have here is this routine. It takes in a number of it reads from a number of parameters that have to be in memory. All of these variables are in the 0 page, so they can be pretty easily accessed. And, why can't I see your chat message in the chat? Barkenbin, I noticed you Racing the Beam, rather. Yeah, this is 6502 assembly. And we keep all of these variables in the 0 page at the front of the of memory, and that saves us a cycle or so for each of them. There's a tiny bit of memory, 256 bytes at the front, where you can easily store quickly accessible. Hey there, Barkeman, welcome in. And so we try to use that for the I haven't filled up the space. We have about half of it left. The C128 kernel uses quite a bit of it, and I want to keep it in ROM, so we have to sacrifice about half of the 0 page. And what we do here is there are two elements to the graphics on this chip. There is the There's the graphical memory, which is 12 kilobytes at the front of memory, so it starts at 0. And then there's the attribute memory, which controls the foreground and the background color, which follows immediately after it. And the attribute memory takes far less space because that's just as many columns wide as you have times the lines that you have on screen. So it only uses 60 by 25 bytes. So it's using about 1500 bytes of memory, whereas the screen RAM is using 12,000. And that's because there is for every 8x8 block that's on screen, you have to use 8 bytes. There are you take a look at how the graphical memory works. Each 8x8 is represented by 8 bits, and there are 8 of those to fill a single character. So you need 16 by 25 by 8 for the screen RAM, which is 12K, and you need 1500 for the attribute RAM, which gives you about 13.5K, which leaves about 3K more or less for the rest. So what we do here is there's a good chance we'll be calling this routine from another routine. I call this routine from the routine that creates the windows or the boxes around the elements. So I save the original X and Y position into some scratch variables before I go along. Then I loop height times width times to fill in all the attributes, because you pass in a variable called color, which you can set before you call the routine, which controls which color is used for the foreground of the text. So you can set the color before you call it. And then it just loads the color into the accumulator. It loads the data register number into the X register, and then calls this little routine that I wrote that writes into the VDC register. That takes care of two things. It actually it tells the register that we're interested in writing to it, and then it waits for it to be ready. The only way to do this on the 128 is to constantly poll the register, read it again and again until bit 7 of it is set, which means that it's ready to accept data. And that's obviously not great, and it's very slow. And that's one of the reasons that writing something from the C128 RAM into the VDC is can be painfully slow. Now, I've read some articles that state that this isn't always the case. You don't always necessarily have to constantly bit at it to wait for it to be ready. In some cases, you can write more than 1 byte to it, and you don't have to wait at all. And one programmer said that if you disable the interrupts before you hit it and just bang 8 byte into it, it will likely work. So theoretically, we could write 1 character at a time. If the routine just turns off the interrupt before it starts, and then just writes 8 characters at a time, and then waits, and then bangs it 8 times again. So I could technically, to try to optimize this routine, because it's actually pretty slow, even if it's just text, we could potentially try to do that. Then we decrement the width, and we keep going until we're out of width. And once we're done with this, we've basically filled the attributes for all of the columns. And then we do it line by line. There is an outer loop which takes care of the lines, which automatically sets us to the correct X and Y positioning in memory by using this little subroutine I wrote, which basically just transfers the memory pointer around. So in the first round, it sets X to whatever X position you came in with, and to the first Y, and then it just slowly moves us 1 line down. Then it fills in all columns that we requested, depending on the width that we selected, and then it just goes on and on until it's done with the attributes. Then it restores the original width and X and Y positions, since we've been dealing with that in the loop and have reset and destroyed these variables. And then it gets going. It uses the string pointer memory address that you sent to it, which is just a pointer to the string that we actually want to print. And it starts at 0. We load 0 in here, so we read the first letter. Then we check if we have a null, and I've made sure that all the strings that we're using are manually terminated with a null byte. Basically the same trick that C uses to figure out how long the string is. Then we store it in the accumulator, and then there is some magic here, which one of them is checking if there's an ASCII value of 13, which means that it will line feed. It will move the line it will move the pointer one line down. This is so we can basically have line feeds in the string itself, and we can have multi-line values in the same string. And it also checks for the ASCII value 12, and if there's the ASCII value 12, it will pause the output and wait for the user to press a key. That's just when you've done something like 8 lines of text, which is what fits into the window. You can have a 12 at the end, and then it will just automatically wait until the user presses a key and then continue. So that's just a little feature I built in. Figured that would save us a little bit of time. And then we slowly go into this. We load the character value into the X register, and I have this interesting way of mapping the ASCII value of the character in the string versus the location in memory, because I figured that we would have issues with this, and I like to be able to do something like this. This is the greeting text, for example. It's just a very long string. Can't even see all of it. Let's see if I can. And you can see how I'm doing this. We just have a bunch of text. Then we have the value 13, so it line feeds. And then at the bottom we have a 0 to terminate the string. And then we have the second string, which has a press any key at the bottom, and then a 12, so it waits. And the way it does this is that it loads the ASCII value of the age, which is an own figure. For example, the big A is 65, so the age is something like 70 something. And there's a table here which maps the low and high byte of the location in RAM for the particular character. So we can just easily call this array and figure out based on the ASCII value exactly where in memory this particular letter is. So this is basically the runs on 256 byte increments. And we started exactly 8000, which is the 16K mark on the C128. And then you have the offset from that particular location for each and every character. And for characters that we don't actually have in the font, we just have a 0 which leads to the space. 80 is the space character, which is basically just an empty block. So for every character that we don't have, we just print an empty 8x8 square. And this is reasonably fast, works reasonably well. And we load that into the car pointer value here, which we then use in this copy loop to load the byte into the data register, so we can actually write it to the VTC memory, and then we just call the register write routine to write it to RAM, and then we advance to the next line so we can write the second line of the same character. And we have to do this 8 times, since there are 8 bytes that represent each and every character, and there are 8 lines that we need to do. So this alone is slow. We need to do this 8 times for every character that we print to the screen. And of course you can have, in those strings, for example, we have 512 bytes. So we have to do this 8 times 512, which is 4096 times. That's a lot of times to be beating this register every time. So it's not fast by any means, but it's not unbearably slow either. Let's see if we can just see how it works. Where's the... Where's the any key? Where's the emulator? Let's see if we have decent luck bringing that up now. It's weird that it doesn't it changes the title of the screen like every second to reflect the speed of the machine that's being emulated, which is pretty terrible. So OBS has major issues capturing it. That still work though. Switch to the 80 column display, see if we can get it to capture it. There it is. Okay. I can't let you see both displays at once, but I can sort of capture the other one as well. Let's see if I can. There it is. There's the 128. And now this is all you get to see on the 40 column display. All it tells you is just switch to the 80 column mode to play the game. And there's the game. And it starts out in this mode where you have to switch to the 2 MHz mode of the Seat 128, and as soon as you do so, the 40 column display becomes unusable. So what happens on the 40 column display is this. That's what the 40 column display looks like when you have the 2 MHz mode active on the Seat 128. Now, there are some games that actually use the 2 MHz mode while the display is in V-blank. So when it's not updating the screen, you can run it at 2 MHz and then you can switch it back once the display comes back. That's sort of a way to get slightly more CPU power for a little bit while you're not actually actively using the VIC chip. But the VTC doesn't have this limitation, so you can run the CPU at 2 MHz at all times. The VIC display will just look like this. And actually in Vice it doesn't look like this. They have some sort of hack which enables it to just run at the 2 MHz and it doesn't affect the video display at all. But the C64K, the emulator I'm using, is apparently more accurate, and it reflects better on the actual state of the 128. All I've done so far is I've made this little routine that prints these windows, and this will be the main game display. This is where you'll see the a pseudo 3D sort of environment, and that's sort of the proof of concept of that is pretty much next on the agenda. Then you have a window that contains all of the actions that we can do, the keyboard keys to press for each of them, and a description of what they do. And then you have this messages display here that has the text, and as you can see now, if I press any key, it will basically clear itself. What I wanted to show you was when we start it up, how relatively slow it is. Now this has been implemented. You can press X to exit and say either no or yes, and if you say yes, you end up in basic again. And cleans up after itself largely. The main game loop is at least there. But, let's watch the screen while I run it, and you can see that it isn't very fast. It takes a fair amount of time to run. I probably need to reset before I do this. Although it largely exits cleanly, it doesn't the basic ROM basically overrides half of the code. You can see how it's drawing, and you can see how it draws when I press the key. It's not super slow, but it's not. You could definitely do with it being a little bit faster. I'm going to attempt to optimize this a little bit, but what I'm largely interested in doing now is trying to see if we can plot something to this display, and whether we can get that working. And I've been trying to think of what's the best way to approach this with both simplicity and of just in general how on earth you would do this, because I've never written code to do anything like this before. And the way I see it, you have this decently large block, something like this. This is the game window, and optimally what we want to do in case we get where we want to go is that we want to have some sort of sky up here. So this would be something like, this would be the sky. That would look very nice, and maybe if we have memory and CPU time, we could even have a few white clouds sitting in the sky. This would be very nice. Then of course you need to have some sort of floor. The floor sits somewhere over here. This is where you see the floor. And if we're lucky and we have some space, we can make some sort of texture or pattern on the floor. This is a decently high resolution that we're using, so we could probably get away with some sort of pattern or dithering to create the illusion of more colors. And we can change the color every 8x8. So every 8x8 pixels we can have a different foreground and background color. So we have, even though we're limited to only 2 colors in every 8x8, we can still have a lot of colors on screen. And where's the... That's the palette that we have. Am I not able to move that around? No. That's the... you can at least see it. That's basically the palette that we have from the VDC. And the order as well. So this is color 0. And this is the last one, color 16. And these are the different colors that we have. Largely it's not a lot of colors. It's largely just 2 shades of the same color. You have a dark and light blue, a dark and light green, a dark and light kind of light blue color. What is basically crimson and pink, although this is largely the same color, just with different hues. Dark and light purple color. Then you have this brown color, the yellow color, and a light gray. So we have a dark and light gray, a black, and then of course you do have a white as well. So that's the color palette that we can have. With using different textures and palettes and lines, you can create the illusion that you have more colors than this, using both the foreground and the background color along with some well-placed dithering. There are ways to make it at least appear decently colorful, and what I've done so far is I have this simple asset that I purchased from itch.io, which is basically just a brick, and I've taken that and I've tested it using different kinds of shading, and it works reasonably well with a multitude of different colors, which is sort of nice. We could definitely use the same block just with different colors behind it to make the illusion of having more stuff going on. And theoretically we could also change the bricks every 8 so we could have differently colored bricks or whatever. And that's perhaps the simplest bit. That's just getting this here. And maybe we can just have 2 of them. Something like this. And that's all fine and dandy if you're just standing in front of a solid wall. That's part of the problem. Just getting this onto the display and getting the sky and the floor printed. That's probably going to be step number 1. And then comes the complexity, which is basically that, of course, you aren't always going to be in an open room with just straight walls. You're going to be having walls and doors on the side as well. And that's where I'm stumbling, thinking of how we could potentially do that using what has to be something that is easily copied line by line. And of course we could just take this wall and bring it into something like dpaint and just use the perspective command to turn it around a little bit. And then we could have something that looks like the side of a wall. That's not really the issue. The issue is how do we effectively copy that line by line so we don't have to spend ages drawing that. And that's probably going to be one of the hardest things that we do, because printing something like a door here isn't particularly hard. You can just have a door block that you could just you could draw the wall first and then draw the door on top of it. I see that as a reasonably easy thing to do. And, in general, I think that's the easiest way to approach it, is draw slightly more than you need and then overwrite it. Now, depending on how slow this is, that might look very bad on the display. I'm not sure how badly it will actually flicker. Well, I somewhat have a feeling that that might turn out to be one of the major hassles. That actually printing this is quite slow. So my thinking is basically that we could set the cloud and the floor using just the attributes. That's very easy to do. So we could start at the memory location that is basically here, and we could just flood half of the window using blue and flood the bottom half using whatever color else we want. That's very easy to do. Then we have basically a window that is half blue and half gray. Or we could plot it towards something like this line and plot it from this line downwards, just depending on what we want to do. In any case, that's the easiest way to do it. And if we then decide to add some sort of texture to it, we can do that by overlaying some bitmaps with the foreground color on top of it. That's at least, we need to set the attributes anyway for the color, so we have to do that anyway, and that's the easiest way to get a solid background, and that's easily copyable as well, because there are 2 copy modes in the VTC. One of them is the block copy, which basically copies a block of memory from point A to point B, and the other one is just basically a filler. So you can point it to whatever is here. We draw something here. You can tell it this is what I want to copy, and then you can tell it I want to copy it 255 times, and it will just take this and write it sequentially over the lines 255 times, and then you can immediately write to the same register again and tell it that you still want to copy it 255 times, and it will do it again. So you can fill basically 4 lines plus at a time, and that means you can basically do this with 8 writes. You could fill the entire display with a solid color with only 8 writes, which takes a very short amount of time. So that's very easy to do, and potentially if you have the interrupts off, you could do it all at once. you could basically just hack it all at once. The only problem is that it takes the chip a little bit of time to actually do the copying, but the chip itself is much faster than the C128. It runs at something like 16 megahertz, so it can actually do something like 12 or 13 FPS on the entire display just by copy. So it's decently capable of doing the copying if you just manage to make things easy enough for it to copy around. Now for this bit, what I'm thinking is, of course, we could just, this is just a 16 by 16 block. So it's just a single 16 by 16 block, and basically this is a single block. And all the rest is just a copy of this same block, or rather, really that's one block. And we could, of course, just copy the single 16 block. We could copy it down, and then copy it here, and then down, and then here, and then down, and so on. What is probably the quickest, however, is to just have it slightly wider, something like 48 pixels wide, but 16 high, and then you can take it once and copy it 3 times. You take this entire block and just copy it here, here, and here. That should be reasonably fast. And you don't have to write each one of these bits individually. What you can do is write the top line. Since you have all of it in the RAM on the VTC, you could write the top line, and then you could just copy the rest of them. So since this is 16 down, you could print one of them, copy it 15 times, and then you could copy basically pretty big chunks, at least 4 lines at a time from this to this. So that's only 4 operations for each of these. So that's only 12 operations to fill this entire area. That's within reason. With the text, you had something like 4,000 operations for 8 lines of text. So you can see that this should be relatively easy to do. The only problem is that it does take the chip a little bit of time to actually do the copying. We should be able to get this. I'm reasonably optimistic that we could do this fairly quickly. The problem really comes when we need to start drawing the sides, because then they have to look something like this. And that's not quite so linear. And I've been giving some thought as to how we could potentially do that in the most optimal way. And I'll continue to think about it a little bit. Maybe we could do something like print this bit first, because this is a full box. We could print the top line and copy it down, and do the same on the other side. We could print this line and copy it down, and then manually fill in these bits just by copying individual pixels line by line by line by line, because this isn't a very big area. Maybe that's the easiest way. That requires the asset to be stored in memory in such a way that you could somehow do this. And I don't see at the moment how exactly I would do that. So that's going to need some quite a bit of tinkering to figure that out. But that's the plan. So I already have prepared where is it? This little sucker. Let me move you around. Maybe I just expand it a little bit. So this is basically a mono or 1-bit version of the asset that we have. And the white bits are simply unfilled. Or the black bits are unfilled, so we can put the background color there and it will just shine through, and the white bits will be filled, and we can put the foreground color there. So to create this, we would put the background color as green and the foreground color as black. And then by simply changing the background color, we can change the we can easily change the color of the wall. That's reasonably easy to do. And this is a decently sized block. I think this one is 48 by 16. It will take a bit of memory in the VTC to do this, and we have to take into account that we only have something like, we have less than 3K of RAM in the VTC, and to be able to use the copy, it needs to be in the VTC RAM. It can only be in the C128 RAM if you want to copy it byte by byte. Or if you want to block copy it, it needs to be inside the VTC RAM. So we need to be able to fit everything that we want to use into that tiny bit of RAM that we have left. That's basically the challenge of doing this. Plus we need to actually get this into the asset file so we can actually access it from the C64 side or C128 side, and it needs to be at some predetermined fixed location, and then we need to find it and plot it to screen somehow again. So let's get cracking. Let's actually do something. Let me draw up the kind of need. Let me just very quickly make a new overlay here. And resize this a little bit so it actually fits. That seems reasonable. Of course, you can't see a single thing I'm doing. That seems to be about it. Okay, we're back in Ubuntu mode. This is the C code that we wrote last session. This time it actually does work. See if I can't make this a little bit more bearable in terms of font size. It's better, right? So this is the code that we use to write the assets. There's a main function here, which you might recognize from last session. Just allocates a bunch of memory. It opens up the files that we need, including the PNG file. I'm going to name this font. And I'm going to name this graphics. I'm gonna pass it in using argument 2. And where's the check if it actually opens. Don't need to free the buffer. There's no buffer at the moment. Okay. Then we have to change this to font. So what this currently does, it just reads the PNG file in, and it gets the pointers to the individual bytes from the struct that we get back. And then we start by writing the low and high byte into the file of where we actually want to read the file in on the 128. This is basically the header of the file, and it just tells the C64 where to place the data. You can manually set that when you load the file, but it's easier to load it with the kernel with these values just set in the header. So it ends up at we set load high as 80 and load low as 00, so it loads in at 8000. That's the start of the RAM where we will have the asset code. And then we just start filling in the font data into the file. And starts by placing just 8 empty bytes at the start. That's the space, and we just generate that here. And then we go through the characters that were loading from the font individually. I wrote this routine that basically just jumps into the X and Y position in the file using the offsets that are there. It's just a bitmap file that has it's just a PNG file that has a number of characters in it. And they're all spaced evenly, so it's reasonably easy to just write a routine that takes a block of them and copies them out. And this routine basically takes the individual bits and makes them into a single byte in the right order for the file. For the C64, I actually have to swap them around, otherwise the characters end up reversed, and writes it out into the out file. And I've commented here exactly where it ends up in C64 space SL, and which, or C128 space as well, and which character is where. And this is basically what the array routine does that we looked at earlier. It just takes these particular RAM values that we're loading the asset into and maps it into ASCII value so we can print it on screen. Now this looks complicated, but at the end it was relatively easy to do once I figured out the best way to do it. This routine that's called put characters is all it does is it creates two empty strings, and then it just uses this print bits routine. All that basically does is take the byte and print the bits out in the correct order. And since it isn't even on it's never on an even boundary, or very rarely it's only in one row that it's on an even boundary, because there's a border in between. So the first character sits at x1, so it's not on exactly the right boundary. So you have to figure out how it's offset between those. There's a good degree of possibility that you might have 3 of the bits in one of the arrays and the other 5 in the other, and so on. And then it just checks where in the offset you are. But you know, based on the x and y, where the offset is, and you can set it at the start. Both the column and the offset, you can set it. It's easily calculated. And then you just jump through this endless amount of if clauses to figure out how to set the offset. If you have the debug turned on, it prints out all of the bits before it compresses it back into a byte, and it just shifts the individual bits back into a byte, and then it glues it back together by ORing all of the values together and places it into the file. And then it resets the offset and does it again for each and every byte that it prints out. Print bits is relatively simple. It just goes through each and every bit and just takes each individual bit and shifts it around. We print it bit by bit. Now let me swap it here. So this eventually we got to working, which was great. Now we need to figure out the next step. I'm fairly sure we need to I'm not sure we even have to close the file. We can probably just open it again. We close the font file here. The graphics file we don't close. I wonder if we could just call these routines again without resetting anything. Maybe we can. Hey there, welcome in. I might do that. I might put it onto YouTube. It's only on Twitch for a little bit, so I will give it some thought. Now we have something in place. Let's find out whether we can actually call this like this. If we can, we should be able to just print some random bytes from somewhere deep in this file. Has 16 rows, so row 13 x 5 13 6 13 7 14 5 14 6 14 7 and 15 5 and 15 6. Let's see if this actually works. Oh, it doesn't. Forgot something in the worked. Let's eventually we'll make this PNG just be like a sprite set into which we'll why is it so wide? Into which we'll put all of the graphics that we want to put in the set. And, right now it's just this single thing. And, I might change the font as well. That's not hard to do once you have the code to do this in place. We can change all of this around once the code works. It's easy work. libpng error png unsigned integer out of range. Okay. Maybe it doesn't reach quite this far. Let's just start by getting something like 3 bytes. Let's take them all out of row 13. See if there is a row 13 in general. No. It doesn't really tell you very much, does it? Doesn't even tell you what it's actually erroring on. It's one of those lines that's erroring at least. This one. No. Okay, it doesn't like this at all. It looks like reusing the same pointer is not a good idea. I guess we should reinitialize all of it. Can't declare it again, that's a bad idea. I can reuse the same variables, just create all of it again. Yeah, that works. And we can add this in again. We got some output which was 19, 1200, 200. One and 200, okay. That's pretty good. So technically, we should be able to do this. Just go through all 16 rows, 48 bytes, printing each byte out, and then after we've printed each row, put in a new line. Then we should basically get a printout of all the values in the file. Yeah, that largely worked. There's too many for us to see on screen. Unless we reduce the font size a little bit, which is why the font size was reduced to start with. Let's see how this looks. This is probably more than enough. Yes, it is. Maybe we can do this. Still seems reasonable. Yep. Needs padding as well, so we can actually read it. And now we need to reduce it again, because the padding adds a bit of width. Still doesn't fit, right? No. Now it fits. This seems reasonable. If we go back to the node cam, no, that seems weird. That seems weird. There shouldn't be a large block of zeros there in the middle. See no particular reason for that. See, where's the go to change this button around. Want to get access to this. Reconfiguring my stream deck a little bit here. I can easily switch between this and this. So, but okay. Let's try to understand what we're looking at here. First real question is, it is 48 by 16. Yeah, so that's the correct resolution at least. That's the correct resolution. This is weird. Let me take a look at what's actually inside. This file called graphics, it does look identical to what we have. This is weird. Why is it like this? Okay, let's trust in what we're doing here. Now, where is the end of the file as we put it? It's at 8268. That's where we wrote the last character. That's at 33,384. I'm thinking whether we should pat this just a little bit. Pat the file just a little bit so it's on a more even boundary. And, we really don't need to, but we might want to do so anyway. Just in case we want to put more fonts in later, might be a good idea to leave a little bit of room for more characters in the font. If we do pat it, I think we would have to pat it all the way to 33,536. That's 152 bytes of padding. It's quite a bit of padding. We'll leave it as it is. Hold on. We'll leave it as it is. And just put it straight after the font. Now, it's nice to keep the debug in case we want it, and we just define the debug at the top, or define it when we call it. Instead of just printing this out, just write it to the file. So now the asset file should have increased in size quite a bit, and that's the case. Game data is now 1386 bytes. Now each 16 by 48 block. Amiga Toronto Gamer. You found game dev. Gain FFT 08B 8B experience. 6502 gold. 6502 gold. We can't divide that. No, there's no divider on the 6502. We have to just shift it around endlessly in a loop. Now, if we use 768 for each of these assets that we put into the VDC RAM, that means we can only have something like 6 of them. So we might have to cut down on the width. But for all intents and purposes right now, let's assume that we have the space to do this and just plot it out there. It might be too wide even to fit 2 of them into the window, but let's see if we can do something about that. Now the build script for the game should build the game and copy the new game data to the correct location. And if we go to the emulator now, we do a little bit of a reset. What is that? You haven't seen the game. We haven't seen. We've made a little bit of progress, or I have. This is what it looks like now. It's not the greatest game in the world, but it's a game. And, it runs in 2 MHz mode, and I can do things like plot text to the screen and have a display. And it looks a little bit like a game. It doesn't look a lot like a game, but it looks a little bit like a game, and it has a bitmap font. And, we still have this reasonably high resolution of something like 480 by 240. So it's not low resolution in any case, and it looks, I think it actually looks pretty good. Yeah, I've spent a bit of time on this, a little bit of time on this. I won't deny that. Well, take a look at the code. I was just going through it earlier. This is just the code that writes the text on the display, and painstakingly goes through there are various things you can set. You can set various variables before you call the jump to the subroutine. The pointer to the string that you want to print, and the X and Y position you want it in, and the width that you have available for the text, and the height of the text area, and the color you want to print it in, and so on. And let me set the foreground color, loop for the width and height of the display, and set the foreground color for the text. We do that first. Then we load each individual byte, and then we have this little trick here to map the individual ASCII values of the string into the place they're placed in the RAM, which is basically this array here. You give it an ASCII value, and it will tell you basically the low and high ID or memory address of where you can actually find a particular character in the C128 RAM. Then it loads it into the accumulator, 1 line at a time or 1 byte at a time, and then it just goes to the next line and writes each character in a row, and then it repeats for every character in the string, and so on. There's a little bit of it can do things like feed to the next line, where if it encounters ASCII value 13, it will automatically just increase the Y position and set you to the start of the next line. And it also supports this next batch thing, which if you place ASCII value 12 at the end, it will automatically pause for input, so you can have a stream, and you can pause it after it's printed out, something like 2 lines. That's basically what we're using it for at the moment. That's the press any key functionality here. These are basically 256 byte strings, and it does wrap, but obviously not on a word boundary, so you have to manually wrap the string if you wanted to. But if you it will never cross the boundary. It will go to the first character on the next line. I've spent a lot of time writing these utility routines to talk to the VTC to figure out where to place the location to get to an X and Y location on screen, and to draw the border, and draw the title of the border, and to be able to print the string to screen and so on. This is all taken quite a bit of time. And what's taken most time is just figuring out the VTC. I struggled with this printout code for a long time before I realized that you do. Yeah, I'm fairly sure it's going to be that case, and because the next thing on the agenda is just drawing the game window, and that's going to be a lot of work. Getting that to work in some sort of pseudo 3D is probably going to be a ton of work. And after you've completed that, writing the actual game is not going to be particularly difficult, I think. And it's still a lot of work, but it's not overly complicated. This just writing to the display was overly complicated. But this is badly documented. And one thing that I stumbled over for many days is that this isn't actually on the correct boundary, because when you set the number of columns, it doesn't actually mean that the display is exactly that many colors wide, because the column is always 8 pixels wide, and in this case we ask for 16 by 60 by 25, but it isn't exactly 16 by 25. There's like a pixel or so missing in each direction, so you can't use the last column and you can't use the first one either, because they can accidentally overlap into the other one. Yeah, it's very easy with the WIC. The VTC is way more complicated than the WIC. It's not complicated at all to use the WIC. You can basically just you can just write it directly into the memory of the C64 in a perfectly logical way. But the VTC is way more complicated. You have this tiny register window that you can write into, and you have to figure out just a routine that sets up the VTC. Is probably one of the most complicated things at all in this. This is the utility assembly subroutines, and contains things like multiplication and division and so on. And this is the init, where it basically we start by jumping to a subroutine which reads all of the registers from the VTC and just saves it into an array in memory, so we can restore it when we exit to basic again, so it doesn't end up being completely destroyed. And then you have to go through each and every register, set the correct settings. Here we move the attribute memory for the foreground and background color to exactly 12,000, which is exactly how many bytes we have to use for the pixel display. We have 16 by 25 times 8 bytes for the pixels, so that's exactly 12,000. And then we have another 1500 for the attributes, which is exactly 60 by 25, because you will only set the foreground and background in an 8 by 8 pattern. And then you have to set the number of columns total, the number of columns that you want to display, the horizontal and vertical positioning, which controls how it's centered on the screen, the total rows that you have in the scan, the character height, and which is 8, and the character width, with and without the gap, it's 7 without the gap, and 8 with it, because you don't want you want to be able to create a solid line that doesn't have a gap in between. And then you have to set the default background and foreground. You have to turn the bitmap mode on. You have to tell it that you want to use the attributes. This is a hack to set the DRAM fresh to 0, which gives you slightly more cycles in the clock, so you can do more things with the chip. And then you have to then I'm doing a little bit of work on the C128 to set the RAM configuration. We need to have the IO space enabled, because we need to be able to talk to the VTC. So this space from D000 needs to be available somewhere in the address space. We enable 16K of shared RAM. That's shared between all of the banks. So we have 16K of code space basically, and then we basically have 16K that we can swap in and out and bank. So that's the assets. Technically, we could have 2 assets bank loaded at the same time. So you could have one dungeon sitting in one bank and another dungeon sitting in another one. You could swap between them back and forth without having to load anything from disk. And it should be fairly trivial to write some sort of code to so that you remember the ID of the dungeons that are loaded. So if you have to go back and forth from a dungeon, for example, let's say you're in a town and you want to access the dungeon in the town, you could have both of them already in RAM, so you could go back and forth without having to assort to loading from disk. But once you exit the town and go somewhere else, then you would have to load. And then you might want to maybe keep the town loaded in the other bank, but to keep the outside area loaded into bank 1, so you could go into the town without having to resort to loading again. That's sort of how I thought we might be able to approach minimizing loading times. But we do have to load some things, and we have plenty of space in the asset bank to be able to load things. And we do have plenty of shared RAM as well, so we could easily have things that are accessible everywhere just stored in shared RAM. At least we still have plenty of space. Who knows whether we will run out. And then it just loads the asset file and puts it into RAM and returns to the main function. The main function is very simple. One of the nice things about the CA65 and most of the modern assembly things is that you can have macros. So I have lots of macros like this. The macro is basically just an assembly routine, and I have this macro called string pointer, for example. All that does is take a single parameter, which is the string name, and it puts the lower byte and high byte of the memory address of the string and places it into the string pointer. And therefore, if you call a routine that takes a string pointer, you can just use this macro to tell it the string that you want to load, and then you can call the routine and the string pointer will already be set to the correct string. Saves you from all it really does is just takes the string name and replaces it with whatever you put here and places this into the code instead. So it's just shorthand, so you don't have to actually write it in each and every time. There are plenty of things like print chords, set screen pointer from memory, advanced memory, which are just shorthand for actually not having to type all of this again and again and again. And there's a routine here there's a macro called draw text, which just takes in all the different variables, the x and y coordinates, the width and the height of the text, the color, the pointer to the string, just fills all of it out and then calls the subroutine. And the draw box as well, which draws the box with all the correct configuration, set bank configuration, which sets the C128 memory bank and so on. That means that the main function can be pretty simple. It calls the init, then it prints the text on the VIC2 display, which is basically just telling the user to switch to the other screen, which is you can see if we load it again. That's the first thing it does. All it does is tell the user to switch to 80 column mode to play the game. And then it's done with the init. It's already loaded the assets and set up the VTC and so on. Then it draws the 3 boxes and it clears out the messages box, and then it prints the megahertz display, which is basically just this little thing that tells the user that we're about to switch to 2 megahertz mode. And of course, as soon as the reason I don't do that immediately is because then the VIC display goes to shit. As soon as you go to 2 megahertz mode, you lose the VIC display. So I'm telling the user beforehand and allowing him to switch over and press the key before that happens. Because when you do press the key, this is basically what happens. And after that, the CPU is running in 2 megahertz mode, and this is where it draws that. Then it draws the action box, which is the box that tells the user which key does what and so on. That's all done with this single macro draw command text, so we can easily just call it to refresh it. If we, for example, switch the actions box to the battle box, then we can just call these routines to switch them constantly back and forth without having to resort to manually doing this every time. And then it prints the greeting text that you see, and then it waits for a key press again, and then it goes into what is essentially the game loop, which is just right now all it is able to do is exit. So all the game really does now is print this single thing out, and you can press X, and it asks you if you're sure you want to exit, and you can say no, in which case it just clears it and goes back into the main routine, or you can say yes, and it goes back to basic. That's basically it. And, this is taking I've spent maybe 2 or 3 hours at least a day, sometimes more on this. And this is where we are after 3 weeks of development. But, I'm still pretty pleased with it because coding in assembly is not easy at all. And the VTC isn't easy at all, and I'm no expert in either of these things, so it's taken me a great deal of time just to figure out basic things. And maybe I had some rough idea about I had done some light reading on the subject before I approached this. Now I'm particularly curious whether we can actually just do this or not. What we want to do now is I want to see if we can write a little routine that we'll call it draw game, and all it will do is RTS at the moment, and we'll just return immediately. And each time we need the ASCII value here. I've decided that we will move around using the numeric keypad on the 128. That seems like the best way to do it. The cursor keys, it has basically the cursor keys from the light reading. There's a few bookmarks in my in Chrome right now where I've documented various things like the weird VTC registers and all sorts of tips and tricks. And pagetable.com is an invaluable resource. It has a ton of de-assembly information and all sorts of tables about every single 6502 assembly command, and the C128 internals, and each and every kernel routine, and what you should set the registers to, and what it returns, and That's been very useful. I've used that a lot. Then there is a mapping the C128, which is also pretty good. It's a solid book that was written 30 plus years ago. Contains basically every single memory location in the C128 and roughly what it does. There are some Abacus books as well that I've delved into a little bit. But roughly the plan is to allow the user to move around using the cursor keys, because while the C128 does have cursor keys, it actually has two sets of them. It has a full set of cursors where you would normally have more of the function keys. So next to F8 there's basically 4 keys in a row that form the cursors, and that makes absolutely no sense to me. And it's not practical to use that to move around, I think, at the top of the keyboard. And it's also not in the regular order that you usually have cursors in. And then it has the default C64 cursor where you have to press shift. You only basically have either up or down based on whether shift is held or not, or left or right based on whether shift is held down. And I don't think that's very comfortable either. So since you have a numeric keypad, I think we'll just use the numeric keypad to move around. I think that's fairly basic, in which case it's 56. The ASCII values we're interested in are 56. That's up. $54. Which would be turn left. $52, which would be turn right. And 50, which would be is back. Forward, turn left, turn right, and back. These are the values we're interested in. Obviously, we're going to have to do something more here. But for all intents and purposes, we'll just call the draw game routine each and every time. Obviously, we're going to need some sort of parameter which tells it in which direction it's going. And ideally, we would want the X and Y position in the map as a parameter. Well, we don't really need that right now. This is just to get something working. And the key that was pressed is in the accumulator. So what we could do right here is just call print integer, which outputs on the WIC display, and all we need to do to be able to do that is not set it to 2 MHz mode. We'll just skip that. I think there's also a print here somewhere. Inside of the wait for key routine. Or maybe it's inside the loop. It's not here. It's not here. It's not here. It's not here. It is active though, you can see it. CMake isn't actually too bad. But it's a massive pain in the ass if you just want to add something. But if you're developing something, it's actually decently easy to use. But if you want to make easy changes to something, that's a totally different thing. It can be very difficult. It's particularly nice if you want to develop cross-platform. And it makes it very easy not to have to run any sort of configurant such things. And, but it's particularly valid if you also want Windows as a target environment. And then it's very easy to integrate CMake with something like Visual Studio. Setting it up is a bit of an effort, and if you just want to change one tiny little thing, it's way too complicated. Yeah, and the thing is, of course, you can't run any of these scripts on a Windows sort of machine, which is, I think, why CMake exists in the first place. That and the fact that most of these tools most of the AutoComp tools are GNU tools. I need to figure out where exactly it's calling the... Could have sworn it was here somewhere. Might also be calling the... What's the name of that? That kernel... Character out, it's called. Yeah. Don't need that anymore. We could pilfer this though. Just use it. Okay. Let's build it. good to call things the right name here. Works better. It's called VDC draw game. It's obviously been a few days since I was working in 6502 assembly last. So I don't remember how to code anymore. There we go. Let's see what happens now. Maybe this is actually a more interesting display. Now if we go into this subroutine that we just wrote, it should print the keys that we're pressing as we press them. Yeah. But you can set things up in CMake to make that easier. You just have to do it. Yeah, I agree. That's one of the things that's... it's not easy at all to add an LD flag or a C flag. So way too complicated to do so. You just want to add a single library that you need to call, or need to add a flag to the C compiler to tell it to do something. So Amyberry is using CMake, and when I ported that over to the Mac, that was a pain in the ass. I spent a lot of time dealing with it, and eventually just modifying it properly so it could actually work properly, and just instead of just hacking it around. That basically required me to make a new build target for it. If you have build targets defined, it's usually easier to just make a new build target and put all of your stuff in there. Let's see what's actually happening here. 8, 4, 6, 2. I've compiled Amyberry many times. It works pretty well on OS X right now, except it works perfectly fine on Intel. It works perfectly fine on M1 and M2 as well, but it doesn't support JIT. None of the JIT emulators work properly on the M2 chip. Why are we getting 4 copies? We should probably be we should probably have a subroutine called move, which just calls this and jumps back, so it doesn't compare it again and again and again. I'm thinking it might be hitting all of them. How do you like this joke? Remember my name? I'm going to loop forever. It's an 80s joke. So if it matches nothing, it just jumps back to the start. It's very easy to get lost in spaghetti code in assembly. It's particularly difficult to try to avoid it. You can, with macros and subroutines, you can do things in a relatively decent way. Let's load it again. I built it again. Yeah, how it works. We want to go forward. We get an 8, 2, 4, 6. Okay. That's fine. And in theory, it's just passing the movement into the routine using the accumulator. So we don't really need to work on that. It does need some sort of type called that joke. Definitely, without a doubt. Okay, now we have that in. Let's work a little bit on this routine. We need a memory location. We should probably store that in constant somewhere. Asset wall, where did we say we were placing this? Some very uneven address. I decided not to pat it for now. It's a little bit of a waste of RAM. We're at 8268. That's where the font ends and where the wall starts. We'll just start by doing this the old-fashioned way. Something like 768 bytes or so. Didn't I have a macro for doing this? I think I did. Let's see. How did I do this at the time? This is the Dropbox routine. It's very complicated. By far the most complicated in this little bit of code. Yeah, that's right. I'm using this thing to map it, and I'm storing it in this car pointer. We should probably make a little bit of space in the 0 page. Call it graphic pointer, and it's just a word, basically 2 bytes. This is not the only place it needs to go. It also needs to go here. That built. That's basically where we'll put the pointer. Might make some sort of similar array here. So we're going to need to copy this eventually to the VTC RAM. That's one of the things that we need to do. But for now, let's not. It's 68. It's 83, 68, right? Let's asset 0. This will come in handy. Even if it takes a little bit of space and RAM, it's still a very good way to do this. I'll steal this code. What did we call this? Graphic bank low. Graphic bank high. And we called it graphic pointer. Low byte goes into graphic pointer, high byte goes into graphic pointer +1. That's basically what we want to put into that. So when we call it, we need to load it like this. It's an indirect. It's the only way to do this. My 8-year-old son asked if he could have a bookmark. I said sure, but a little upset that he didn't know my name is Brian. That's very good. Very good. Go away. Let's see. Some sort of loop here. Some sort of loop. I'm going to increase Y. And probably check for overflow. I think that's the simplest thing to do. I want to make this quick and dirty. What's that called again? Branch. On the overflow bit. Branch on overflow set is BVS. Otherwise, go back. Put done here. So we will just, this will execute 255 times. Basically, we'll load the graphic pointer. Increase Y by 1. If it overflows, in which case we've done 255, it will go to done. Otherwise, it will jump back. Now, what we need to do here is go to the correct X and Y position. So we want to jump to set VTC memory address to XY, which means that IPOS and XPOS need to be set here. Or does it really? Can we just... We know where it is, right? That's not going to be something that changes a lot. Can we just set it? I don't remember exactly where it is. It's at 1, 0, so it's at 2, 1. Just load those, store them, and then we can call set VTC memory address to XY. And it will move the memory address of the VTC chip to X2, Y1. In which case it's set at the correct location, and we'll load X with the number of the data register. That's the one we'll be executing with. And then we'll just, once we have the value in the accumulator, we can call VTC register write, which will take whatever's in the accumulator, just show you what it does. Faster than trying to explain it, I think. It's a short routine. Is it in the utils? Might be. No, it's here somewhere. Here it is. those 3 routines basically. So what register write does, it takes whatever is in the X register and stores it into the register selector, which is at a fixed address, which is exactly D600. And that's stored in a constant somewhere else, so I just call it VTC state register. And then it enters into this loop where it checks for bit 7 of the VRS. And if bit 7 is set, then it's ready to accept data. And if it's not, we just branch back and loop infinitely until it's ready. And once it's ready, we store whatever is in the accumulator into the register of the VTC that it's set. Then we have something called register read, which basically does the same thing. It sets up what we want to read for, waits until it's ready, and then loads whatever value is in the register into the accumulator and returns back to where we were called. And then I have this third routine, which just readies the register but doesn't actually do anything with it. So it's you can call it outside of the loop, for example, and then you can hit it once you're inside the loop. Saves you a little bit of time if you just need to call it once. Let's get back to the business at hand. I've tried to split things into different files, so don't have an endless amount of stuff all in the same file. This file is already very complicated though. Contains all of the graphics routines. Might split it up further than I already have. It's already difficult to find stuff in it. Let's draw text. Here's draw game. So we'll call the register write, increase the Y, branch to done. When we're done, and jump to the L. This is not enough though, because what we haven't done here is it's good to comment, because when you come back to the code with assembly, you have no idea what you were thinking. So if you don't comment, you are absolutely lost. You already sort of decided what we wanted to do with the attributes. So we wanted to fill half of the screen with or at least the first X lines with blue for the sky. So let's go back to main here. How many lines are there? There are 13 lines. There are 13 lines. At the moment, we can of course change this. The messages box sort of needs to be where it's at now, roughly 8 lines of text. So can't really afford much more. The border takes a line. 2 actually, one at the top and one at the bottom. So we have 13 lines total. Four for the sky, 4 for the floor, 7 for the wall. Roughly. give or take. That's 15 though, right? We only have 5. Three, 3, and 7. Probably. So we'll draw the top 3 for the sky, the bottom 3 for the floor. Okay. We'll take a look at the palette again. Figure out what palette colors we need. The light blue, we're thinking of 3. And for the dark gray, we're thinking of 1. Floor color. Sky color. Wall color. Let's put the wall color in as I think it actually looks pretty smashing with a 6. For now, we'll just put this, have this, do this in a very simple fashion. How many do we need? We start at 2. Axis 2 when we get in here. How wide is it? It's 32, of which 1 is at the end. It's 29, right? Times 3. It's 87. Order in which we do this does not really matter. So we'll call set attribute address to XY, which is basically the same function as set memory address, except it sets it to the correct memory location for the attributes. Then we'll call this loop 4. This is loop 1. We'll prep the data register here. Load color into the accumulator, because that's all we want to do. Actually, what we want to do is we want to rotate it as a background color, not a foreground color. So what we want is 30. Background is in the upper 4. No, that's a lie. It's reversed. So 3 is correct. That's the background. Foreground is in the upper ones. The other one is in the lower ones. So we have the X loaded with the VDC data register and the color stored here. So all we really need to do is write the register, and it will automatically move memory accept. Accept. DY. And then BNE to L1, branch if not. That's what we want to do. And then after, we basically need to do this 3 times. We'll optimize this later. We need to do this 3 times, and we need to move increment Y position in between each of them, because we want to start at the start of a line. Oh, we want to do it like this. This can obviously be optimized quite a bit. I will do for a rough test. That should be 3 lines of the sky. Let's see if it actually does anything. Good thing about copy pasta programming is that if you make an error in one place, you have multiple errors because you've pasted your errors all over the place. That's nice. It's very nice. Just jump over here and reset the 128. Load the game from disk. That worked well. Sort of did something to start with. Let's take another look at actually what happened there. It doesn't do anything until we press up. It sort of did something, and then it overrode further into attribute RAM, and that basically just destroys the display. So there's obviously some sort of error in that code. Let's debug a little bit. What did we do wrong here? We're at 2.1, that's right. Saved it into X and Y pos. Set that here. Might be smart to do it this way, in case the Y is overridden in some way. That might be the case. There are only 3 registers. There's no guarantee anywhere that in some functions I'm very careful not to override the registers, and others not so much, because you only have 3 of them and you have a finite stack in which to write them. You don't want to waste a lot of memory with temporary areas of memory to store old register values. So for some routines you just sort of have to expect it to be empty when you get back, or be trashed. The stack is pretty small, and you can only really push the accumulator there. So you can push the accumulator back and forth, but the stack is just a few bytes. Still does this. So that's not it. It might be this code. The pixel drawing code, that might be the one that's crapping out. Let's comment it out, build again. Yeah. Okay, so this attribute filling code seems to work fine, except we need to push it one further. This needs to be 30, 30 and 30. And what I'll probably do actually is I'll just write the first line and then copy them. That's much quicker, but for now we'll just leave it like this. So that's what we want to do here. Also notice that this is not the correct color. This is not the color we wanted. Which is a bit weird. Let's test this a little bit. Fairly sure I had the correct value. Let's do this. I switched the console of 128 into 80 column mode. Weird. Still dark gray. Build. Reset. That's interesting. It's writing some sort of pixel every time we... Yeah, it's probably because we're asking it to print the character we're pressing on screen. So it's calling a routine and it's just printing a single pixel on the screen. Okay, but why is it dark gray? Ah, right. I know why it's dark gray. I know why it's dark gray. That's because we're loading the address and not the value from memory. Still dark gray. That's nice. I think I know what's going on here. It's only loading the correct color in the first loop. So it's only the top line that's actually taking the correct value. Yeah, so now that's black. Let's test this theory. And then fix it. Yeah. Now it's dark blue. A reason for this is that the set VTC attribute address to XY overrides the accumulator. So the color gets set to a different value. So for the subsequent lines, always dark gray, because that's the what gets loaded into the accumulator. It's probably the Y position. See. It's getting pretty late to finish this attribute code. See if we can't write the pixels to the screen as well. Call it a night. Why isn't it? Why is the background color not working properly here? You shouldn't program in assembly language when you're tired. Sort of a dumb idea. It is setting the foreground color correctly. Okay. I think I found the issue. It's just nice to be on the 80 column screen with our load as well. let's just don't have to constantly switch between the displays. Yeah, that's more like it. It's not the correct blue, but it's it is the correct blue. It is 3. I'll have to change the border of this one to something else. It's easily done. That's easily done. And, okay, we have the three lines there. Let's do the floor. Let's do the floor next. I'll call this all these 7, 8, and 9. The bottom one that draws this is going to be 10 then. So I also want to the wall color is going to be 60. The floor color is going to be 10. No, not. Yeah, 60. Yeah, black foreground, green background. Or, yeah, close enough. That's roughly what we're going to do. We increment the Y positioning here. We do three more of these loops. Call this one 4, 5, and 6. And for the floor, we actually need more of them, right? We have, how tall was the wall? We made the wall. A total of what, 13? The middle part is 7, roughly. So we need way more loops. It's only 3. Four. Five. I'm doing row 10 now. That's the last one. Then rows 11, 12, and 13 are the floor. Wonder if that compiles. It does compile. See if it actually works. Sort of. Forgot to increment the Y positioning here after the blue lines to fix that. Now we did increment the Y positioning, but we did not remember to call the set attribute after we did so. Probably the same problem then. Yeah. Need to increment and we need to set the attribute address. See how that looks. You notice that this is decently fast because it isn't really, despite all the writing. That's okay. Okay. It's roughly what we want. Now we're just missing the wall over here. We obviously need to restore the original X and Y position. Just easier done by just loading it in again. We know where we want to be. We want to be roughly at, what was it? 1 is the top, 2, 3, 4. 4, 2, that's where we want to be. And this is loop 14. Now I need to check whether increment Y actually sets the overflow flag. No, it doesn't. Does set the N flag. Does set a negative flag if it goes to 128. So we can use BMI branch on result minus. That means it only loops 128 times. That's enough for now. Let's see if it actually works. Then it doesn't. What would have been happening otherwise? It just goes on and on until it's out of RAM, because the as long as you're writing to the VDC memory, it automatically increments the pointer. So eventually, it just reaches the end of the 12K of pixel RAM and overwrites the attribute RAM. Then it reaches the end of RAM in general. And then it just gets stuck. That's something. It's definitely something. wrote something like the first line, then of course we forgot that we need to go to the next line. We can't just go on and on because then we override the actions window. Oh, it's started here, then it just continued over here because we need to let's start with 0. How wide is it again? It's something like 30, right? So if we compare the Y, we need to use branch on result 0, which gets set if they're equal, and it just does the single line. Ideally, we would want to loop this again and again, but technically we would be copying this anyway. So we would need to advance the graphic pointer once we do this. If we do it like this, it will basically just draw the first line and leave it there. And then I'll write the rest of the code to copy the line and optimize this code. And I will return to this next week. Where is the... Let's see whether it actually writes the top line now. Shouldn't really do anything else. Can't really tell whether it did or not. Doesn't really look like it did. Where are we setting the location in RAM to call this from? Where did we do that? Here. Best to keep this code. One obvious thing here is that we forgot to read 0 into the X register. We have no idea where it's actually fetching this data. See if that makes a difference. Pretty much the last thing I try. what I wanted to do. Why are you being weird, Mr. Stream Tech? Why is it doing this? Weird. One thing that does confuse it is that the title of the window keeps changing. Oh, it's still the same. Okay, we'll get back to this debugging at a later date. There are 5 of you here. Should we raid someone? Maybe. Who? Mantle Ferox. Game Squad. Let's raid Mantle. She's fun. I'll set it up. Barely meet the minimum for me to raid. I'll set it up anyway. Back again here Friday. I haven't decided what we're playing on Friday, but it's going to be from LucasArts. Until then, guys, have an excellent rest of your night. You sleep well. See you here on Friday. Later.